So it starts with nonlinear. Nonlinear is obviously meaning not lines. So think about all the functions that we have done so far in chapter 2. Quadratic, polynomial, rational. They're not lines, they look like curves. Okay. What things come to mind when you hear in math inequalities?
Yeah.
Greater than and less than. Greater than or equal to, less than or equal to, right? Anything else? Like, what else do you do when you're working with inequalities? Kristen? Oh, yes. Open circle versus closed circle. Anything else? There is a rule, change signs if you multiply inequality sign, I should say. Multiply or divide by a negative. That probably won't affect us very much, but yeah, there is that rule that a lot of people remember, so that's good. Anything else you did when working with inequalities?
Like the direction of the line.
Yes, so there's some kind of, can I call it shading? Because you have to, like, after you do an open or a closed circle, then you have to, like, follow the line in one direction to say what are the actual solutions. And so Kristen's really thinking about it on a number line, right, where you just have one set of numbers and you do open or closed circles. If you did it in Algebra 1 as linear inequalities, it would have an x and a y. And so you would graph lines. Do you remember when you had to choose if your line was solid or dotted? And then you had to decide, like, should I shade above the line or below the line? Okay, so that's another way to see your inequalities.
Yeah, wasn't that in like
It could have been.
I don't remember that at all.
I like vaguely.
Okay.
I remember we learned it at some point in
I guess the big idea there is that in an inequality, there are multiple solutions, or there's like a larger solution set that works. There's not just one number that is your answer, right? There could be a lot of numbers that make things less than or greater than some values. The big change for us is the things we're talking about are no longer linear, but they're going to be those curved shapes. So we're going to talk about and kind of come up with a plan for how we can answer these questions. On the first slide, I have 3 pictures of graphs. And I want you and your small groups to have some discussions. I want you to look at each graph individually. So it's not like you're choosing one graph. You're looking at them. There are 3 examples. And I want you to have a conversation. There's 2 main questions you and your group should discuss. First, when is f of x greater than 0? And when you answer that, you'd be thinking in a set of interval notation. And the other big question to think about is, what were the key numbers that appeared in your answer? So when you're looking at the graph, what kind of numbers were special and showed up in your answer? Now, to help you with those things, there are a few extra questions you should talk about with your group. I think the number one thing you have to do right away with your small groups is decide, what in the heck does f of x greater than 0 even mean? So what does that mean to you, and what does it look like on a graph, because you have pictures of graphs. So you need to be able to point out when f of x is greater than 0. And then also to answer the second question, think about when does f of x change its sign from positive to negative or vice versa. Okay, so that'll help you pick out your key numbers. So remember, you're not choosing one graph as an answer. You're looking at each graph as an extra example. Okay, so when is f of x greater than 0? First figure out what f of x greater than 0 means. I'll come around to your groups in a little bit. Discuss. Y, so f of x greater than 0 just means y is greater than 0. And what does y greater than 0 look like on a graph? It's above the x-axis. So I can now go to all 3 of my graphs and I can say, okay, here's a little chunk where I'm above the x-axis. F of x is greater than 0. Here's a chunk where f of x is greater than 0. And then it happens again over here. And then on C, Do I have anything greater than 0?
If you look super.
No, it's supposed to be at 3.
Okay.
Sorry. I agree, it does look like it could go up, but it shouldn't. It should be at 3. Okay, so you can kind of pick out a spot. Now, for C, if there is no interval, you can say like none, not applicable, doesn't have one, something like that. Also, mathematicians like to use this 0 with a line through it, and you'll hear me refer to this often as the null set, which just means the empty set. There is no answer. So when you write that, you mean the same thing as none. So that's okay, you can use that. It's different than 0, right? It's the null set. Okay. Over here, does someone think they have an interval notation for that green piece, Bailey?
Parentheses, -3, comma, -1.
Okay, so she's answering on the x-axis when we'll see y appear above the x-axis, so when it will be positive. Why did you choose parentheses for your interval notation?
No,
It doesn't. It doesn't include. Parentheses are exclusive, so we're saying at -3, it's not greater than 0, it's equal to 0. And same thing for -1. This would be like open circles. We don't want to talk about those specific points. We're going to talk about the points above the x-axis. Okay. What can we write for B then as our intervals? -3 to 0, and we use parentheses for both of those because we don't want to be equal to 0. Union. 2 to infinity. That right side is going to continue rising towards positive infinity, so it's always going to be positive. Now, what were the key numbers that popped up in your interval notation? What are they on the graphs? Very good, x-intercepts. So think about that. At x-intercepts, those are the locations where you can cross the axis and your y can change from negative to positive or positive to negative in a polynomial. So those are going to be what we call key numbers. I'll give you a minute to jot down the steps for solving polynomial inequalities. Then we'll run through them together and we will do an example. So as you're finishing up the last step, it's really important to start by making sure one side of the inequality is equal to 0. That's true when we're solving polynomials. And since we're going to try to find the zeros or the x-intercepts to be our key numbers in part 2, you've got to make sure one side's set equal to 0 to begin. So move anything off at the very beginning. After you do that, you should be able to factor these polynomials to find your zeros. I'm not going to have you solve a polynomial in this particular section by doing rational zero tests, guess and checking, working through all that. That's a lot of work, right? So to find the zeros or the x-intercepts, they're going to be those polynomials that you could probably factor. Okay. After you get your key numbers, you think about that as like those are the different places on the x-axis where I can cross the x-axis and change my sign. So I need to start testing x values to see where the graph is positive or negative. And I'll show you how I like to do that. You can also use what you know about graphs to help you here. Finally, you should write your answer. When you write your answers, there's really 2 answers. There's the interval notation of your answer, and then there's your answer on a number line. So that would be like what maybe Kristen was referring to in our like reminder of inequalities, where you would say like x is greater than 5, and then you would plot an open circle at 5 and shade to the right. Okay, so there's really 2 pieces to an answer. Let's look at an example so you can see this put to work. Our example is x cubed minus 3x squared minus x is greater than -3. So step 1, you tell me, add 3 to the other side. X cubed minus 3x squared minus x plus 3 greater than 0. Should not start solving for your key numbers until one side is equal to 0. Since this is a polynomial, we should be able to find our x-intercepts by factoring. It's got 4 terms, so we're going to use factor by grouping. So group my first 2. What can you take out of x cubed minus 3x squared? An x squared. You're left with x minus 3. What could you take out of negative x plus 3? -1. Always make sure you take something out of those last two terms. If they don't share anything in common, then you should take out a plus 1. There has to be an operation sign and a number outside that second group. And that leaves me with x minus 3. Note for future reference, if these two parentheses don't match, x minus 3, then it's not factorable. So you should stop or recheck your work. But these match, so one of my factors is x minus 3. The other factor is x squared minus 1, which can factor again, right? That's the difference of perfect squares. X minus 3 times x plus 1, x minus 1. You could stop at the second to last step right there and set x squared minus 1 equals to 0. Just remember when you square root, you'd have to add the plus or minus. So we have three key numbers, okay, or x-intercepts. They are 3, -1, and 1. Those are opportunities for our graph to cross the x-axis, because they're x-intercepts, and change its signs from positive to negative. Okay, that's where that can happen. So all I'm going to do up here is draw a number line. I'm going to put those three numbers in order on my number line. And then I need to start checking the intervals for like what their sign is. Are they positive or negative in that interval? Okay. So I might check something between -1 and 1. What's a good number to check right there?
-0.
Oh, I would choose 0. That seems easy to me. Okay, so I choose f of 0. Now, here's what I'm going to do. I don't really care what the actual value of f of 0 is. I just want to know about the sign of f of 0. Is it positive or negative? So I'm going to come to this place where I have factored everything. And I'm just going to think about if I plug 0 into each factor, what sign do I get? 0 minus 3 is negative. 0 plus 1 is positive. 0 minus 1 is negative. So that means I'm taking a negative times a positive times a negative, which is a positive. So all the numbers, all the y values between -1 and 1 are all positive. You only have to test one number. I could test another section. Maybe I want to check in between 1 and 3. What could I check in between 1 and 3? 2. Again, I'm not actually really concerned what the actual f of 2 is. I just care about whether it's positive or negative. 2 minus 3 is negative. 2 plus 1 is positive. 2 minus 1 is positive. So that would be a negative times a positive, which is negative. Now, that should make sense to you because all of your zeros showed up only one time. 3, -1, 1. So they all have odd multiplicity. What happens on a graph at odd multiplicity? It crosses the axis. What happens at even multiplicity? It bounces, it turns on the axis. So if you have even multiplicity, you could have a negative right next to another negative section. But if you have odd multiplicity right there at 1, it has to cross the axis. So it should go from positive to negative. Now you can use a little bit of reasoning here. What should it be on the right side then? Should be positive. Okay. You could think about odd multiplicity is going to cross from negative to positive at 3. You could think about end behavior. This is a positive leading coefficient, so the right side would be rising. That means this far it has to be in the positives, okay, because it won't cross again. Or you could test another number like f of 5, which would give me positive times positive times positive, which is a positive. So you have a few different ways where you can figure out what to find.
Where did you get the positive?
I'm plugging them into this number.
So I understand you got the negative, positive, negative, and then plugging them got positive.
Oh, negative times a negative is positive times a positive is positive.
Oh, okay.
Yeah, just your rule about multiplying. Okay. And then what should be true on the left side? Should be negative. That was another odd multiplicity. The left side is falling, so it should be in the negatives. Or you could test some number less than -1. Sometimes I like to test on those sides, like super outrageous numbers, like -100. because then I can see negative, negative, negative. Right, that's really easy when you plug negative 100 in. So negative times negative is going to be negative. So you've got to decide what's happening in all sections. Now you've got to answer your question. You want sections that are greater than 0. So you're looking for the ones that are marked positive. What is happening at the actual points we have? Negative 1, 1, and 3. It's crossing the x-axis, so it is 0, right? These are your zeros or x-intercepts. So should those numbers be included? If you want to be greater than 0?
No.
No. So you're looking, where am I greater than 0? Between negative 1 and 1, that's positive. And then after 3.
Is it everything after 3?
Yeah. There's no other place for it to cross the x-axis because there's no other x-intercept. So then I can write my answer in interval notation. That's really easy once I have looked at that graph. It's just negative 1 to 1, exclusive, 3 to infinity. Now, I'll accept, if you have this in your work, I'll accept this as your graph. You can also, like if you check in the back, they'll make a nice graph at the end. You can draw a graph right here. Looks like that. So instead of open circles, I would use parentheses on my graph. It's just a pre-calculation. Does anybody have any questions about that? Okay, so we have one other set. That's going to be the rationals. So I'm going to give you just a few minutes with your groups. You're going to look at a new set of functions. And you're going to come up with the interval notations. I changed my inequality just a little bit. Now I want to know when f of x is greater than or equal to 0. So have some discussions with your group. When are these graphs greater than or equal to 0? I'll help you out.
I would say like that's 2
Oh, because it can just barely get 2 excellences, yeah. 2 infinity? Negative 1
There are, but it doesn't matter. Okay, we've got some good discussions happening. Let's kind of come together and see if we're in agreement here. Does anybody have any intervals for A? When is it greater than or equal to 0? Negative infinity. And then a bracket at negative 1. Why are you putting a bracket at negative 1?
Yeah, no, you're right. I got money.
That's when it's equal to 0. So that works. Any other places? Yes. The other interval should be
2 to infinity.
2 to infinity. And I kind of put the answer there. Why would we use a parenthesis for 2? It's the asymptote. Is there even a graph at 2? No, so there is no positive or negative value there. So don't include 2, but everything after 2 is going to be positive. Okay. Now there is a horizontal asymptote there. It looks like y equals 1, but that's not going to affect like the change in sign. It'll just keep that positive on the other side. So we're okay. What about B? Where did you start?
Parentheses, -1, comma 0, bracket.
Okay, so don't include the vertical asymptote at -1, but everything after it up until your first x-intercept, which is 0. Okay, and then 5 to infinity. So what numbers ended up being our key numbers here? Asymptote, vertical, and x-intercepts. Do we really care about horizontal asymptote at all? No, it's not going to change the sign of my function. So here are your steps to rational inequalities. As you're jotting them down, know that I've specified them for rational functions, but really we're trying to do the same things that we did with polynomials. Set our function equal to 0, find some key numbers where our signs can change, and then find out what the sign is in between them. That's like the basics. Now I did add in number 2 some specifics for finding your t-values. Those are really tips and things that we used in section 2.6, right? Find the x-intercepts, a shortcut would be set your numerator equal to 0. To find your vertical asymptote, always set your denominator equal to 0. These are going to be problems where you don't need to go through all the work of finding poles and things like that. They're going to be pretty basic, like the polynomials you can factor. So find those things. You might have to factor either the numerator or the denominator to find all intercepts or vertical asymptotes, that's fine. Notice that in number 3, when you're testing the intervals, I said pay attention to the vertical asymptote versus a 0. That's why on the previous one I wrote like for each of my x-intercepts 0, 0, 0 on my number line, so I knew that the function was actually equal to 0 there. When I do the rational function, I'll write 0 or undefined. So I'll remember at all the undefined to always use parentheses. There is no graph right there. Okay. And then you can write your answer 2 ways, in interval notation and also like the image on the number line. Let's look at an example and stay with me here at the beginning of the example because we got to do some changing to the function in order to make one side equal to 0, and I want to make sure everybody's with it. So we've got 3x minus 1 over x minus 3 is less than or equal to 1. You tell me the first step is subtract 1. 3x minus 5 over x minus 3 minus 1 is less than or equal to 0. That's an issue for us. All the things we practiced in section 2.6 were just like numerator over denominator. Nothing was added or subtracted on the back of the function. So all the rules that you have in section 2.6 don't apply to this because we have this minus 1 hanging out back. So what you need to do is think about combining these so that it's just one numerator, one denominator. Think about this one as 1 over 1. In order to be able to subtract these two fractions, what do you need? Common denominator. A good common denominator would be x minus 3. So I'm going to have to multiply this number term by x minus 3 over x minus 3. I would call that the well-chosen 1. X minus 3 over x minus 3 is 1. So it's going to change the way it looks, but it's not going to change what it is. That's okay. That's why it's super annoying. Keep your denominator, x minus 3. So when you add and subtract, you keep your denominator. In the numerator, you'll have to combine the like terms. This is really like negative 1 times negative 3, so negative x plus 3. And then just do 3x minus 1x is 2x, negative 5 plus 3 is negative 2. And then it's less than or equal to 0. So that to me would be the hardest of the rational functions when you have to move a number to the other side and then you've got to combine the two fractions through common denominators. But now we're ready to go. We got to find our key numbers, right? X-intercept, set your numerator equal to 0. You could factor this, but there's only one x, so it's pretty easy. Add 2, divide by 2, x equals 1. For my vertical asymptote, set my denominator equal to 0, x minus 3 equals 0, so vertical asymptote is at 3. On the number line, I'm going to put 1 and 3 there. Remember, at 1, it's the x-intercept, so it's actually equal to 0. At 3, it's the vertical asymptote, so it's undefined. Questions so far? Things I need to clarify? Now you just got to test the interval. The interval testing I do is kind of the same. What I focus on is what's the sign of my numerator going to be divided by the sign of my denominator. Same sign, it'll be positive. Different signs, it'll be negative. So I might test f of 2 right here. If I put 2, and I'm going back to the simplified version right here when it's less than or equal to 0, if I put 2 in the numerator, it'll be positive. If I put 2 in the denominator, it'll be 2 minus 3 will be negative. So it'll be positive over negative, which will give me negative function value. Then I could check something in this interval. Let's say I do f of 10. Positive, positive. Right, that's easy to see. So that's going to give me a positive section. And then I could test something over here, f of 0 maybe. Negative, negative. So that's a final step would be answer the question that's being asked, less than or equal to 0. So I know that I'm going to be including 1, and since it's less than, I want the negative section, and then I'll exclude 3. So I would do bracket, parentheses, shade in between. And by coloring that in on the number line, it basically tells you how to write your interval notation, right? 1 inclusive, 3 exclusive. Okay. And if you want to clean up your number line, it would be as simple as this. Any questions? Less than or equal to 0? Read your inequality right here. Do you agree with me? So I chose the negative section. Any other questions? Okay, you do have a homework assignment from the textbook. And I'm passing back your quiz now. Let me get to the next slide. This quiz is graded in green, and I did give you a grade at the top of the quiz so you kind of know where you're at, how many points you would lose if you did the same kind of work on a test, etc. But this is not in the grade book. And I'm not going to put the quiz specifically in the grade book. So, does Ms. Conti think you should do quiz corrections? Yes. Why wouldn't you go back and retry the problems that you missed in case something like that shows up on the test? Is Ms. Conti going to grade your quiz corrections? No. So you're not going to be turning those back into me specifically. Okay? But I do think it's worth your while. What you are going to turn into me for a grade is my follow-up assignment that is 2 questions. So you will complete these and turn them in tomorrow. So right at the top tomorrow, at your gold sheet, at your agenda, 2 questions. I will grade these questions 1. And the question will go, or the score will go in the grade book. So use the feedback of the quiz to help you answer these questions. This is going to be tomorrow, 2 questions. It's a writing polynomial and a graphing matrix. So this will go in your grade book.
Well, I'm gonna feel like correcting.